off and started at the beginning of the semester is that we kind of make the assumption that everybody knows how to draw structures and kind of ignore a whole lot of information. Both the textbook does this and other classes I've been in do this as well. So I've tried to double back to make sure you guys know how to draw your structures and to watch out for them. Okay? But it's going to require practice. Okay? So you're going to have to keep coming back over it. The introduction of resonance as a topic is also a challenging topic. And you don't really get to see the meaning of it until you start looking at reactions. And really reactions where it matters, which is kind of in second semester. But if you try to learn resonance in second semester, it becomes very problematic. Okay? So we're addressing these topics early on to get you practicing with them so that you can find those failures and learn how to advance from them now and then do really well later. Okay? So with drawing organic molecules, if you were all asked to draw C5H12, okay, which I'm sort of officially asking you to do, and now that you finished drawing it, you probably drew just a straight line, okay, of carbons. Okay? But I didn't actually want a straight line of carbons. I wanted a branched chain. Okay, well, the formula doesn't give that information. That's why we introduce structural formulas. Okay, the structural formula breaks down those pieces and now says let's kind of condense them a little bit so that we can better understand how those atoms are connected. Okay? The only reason we use the structural formula is because of typewriters, okay? Or really the technology age and typing in general, or computers. Okay? Because if we asked to provide the Lewis structure every single time, we wouldn't be able to type that very easily. We can draw it relatively quickly, but that's not easy to type. So if I was going to write up a report, I would tend to use the structural formula. With technology advancing as it is, we're going to start seeing, I think, personally, the structural formula, okay, or condensed formulas disappearing from the literature because there's no need to show that. Okay? That formula loses the information that's stashed in the image, okay, or in the drawing of that structure. Okay? So I think it makes more sense to draw out our structures, which is why in this first section, whenever you see a formula, you should immediately convert it into a structure and evaluate what's happening within the structure, not the formula. Okay? That gets taken a step further because then we move into VSEPR. Okay? Lewis doesn't tell you where those atoms are relative to each other. It just says how they're connected. Valence shell electron pair repulsion theory went through and said the individual shapes. So we could better show that structure by throwing in all of the wedges and the dashes, where the wedge meant coming towards you, the dash meant going away from you. Okay? I would love to say there's a default standard on that wedge shape, but there's not. If you have no idea what that is, just draw it the way I'm drawing it and you'll be fine. Okay? So the issue with the VSEPR structure is that still has lots of stuff stashed in it. Okay? And we want to simplify that further, because if we were asked to draw a DNA molecule, okay, anything in biology, any of your biology classes attempted to show the actual atoms in their structures, okay, we would lose a lot of biologists. Okay? There's so much stuff there we don't want to look at it. So we simplify down to potentially a line angle / VSEPR. In this case, really the only thing I've done is implied the carbons. Okay? Because carbon makes up nearly everything we do in OChem and virtually everything we do in bio or biology, we can just go through and assume that points become carbons, and that can simplify our life. Okay? We still have all the wedges and the dashes shown on there, and we still have all the hydrogens, which can also get very tedious to go through and draw, which is where we end up with our final version, kind of our line angle abbreviated. And here we've got our basic carbon skeleton outlined. Notice all of the hydrogens have disappeared. They have now become implied to the structure. Okay? And that, in and of itself, simplifies and makes our drawings look phenomenally cleaner and better. However, again, we've now hidden information. Some of that information is super important, some of it isn't. Okay? And a lot of that depends on the situation that you're looking at. Okay? So we have to remember that those hydrogens are there, and when they come back and haunt us, I will remind you to be thinking about those hydrogens. Okay? So when you look at OChem, which of those 4 formulas should you be trying to draw and mimic for all of your drawings? Okay? Nearly everybody's going to jump to the line angle abbreviated. Why? It is easier to draw. Okay? Probably one of the best students I've ever seen or worked with in an organic chemistry class. Nearly perfected every single test he ever took, including the ACS final. Drew everything as the VSEPR structure. Not VSEPR abbreviated, VSEPR structure. Everything. So when people talk about, oh, there's not enough time on a test. Every time he saw a structure, he had to draw on the hydrogens, he had to specify all those locations. Okay? It all comes to how you process the content. He spent his time learning how things worked, so he could then spend on the test drawing in all the individual atoms. Okay? If instead you're going to be focused on getting through the drawings as fast as possible and hoping, you're okay, I thought there was a computer behind me, drawing as fast as possible and memorizing the content, okay, then you want the shortest drawing possible. Okay? And it really comes down to where you spend your time and effort. Okay? So, simplifications. In OChem, we really have our 8 elements. We have simplified shapes and hybridizations. We haven't talked about hybridization officially yet. We'll come back to that. And then we have our abbreviated drawings. These 4 bullet points are insanely important to acknowledge. Okay? If you ignore these 4 bullet points, you will have a horrible time in OChem. Okay? And that doesn't have anything to do with actually then moving into manipulating these structures. That's just saying you have no idea what the structures are showing. Right? So every point is a carbon unless otherwise specified. Right? So if I don't want the point to be a carbon, I have to say what that atom is, period. Okay? Hydrogens are implied to carbon to satisfy octet. Does that mean they're always implied? No. Right? I can show all the hydrogens if I want, but if I want to abbreviate, hydrogens will be implied, and only to carbon, not to any other atom. Right? And so they will be implied up to the octet for carbon. Right? Rule 3, charges are never, ever, ever implied. Right? The reason being is we've already implied hydrogens to satisfy octets. Okay? So if we start implying charges, we're now confusing whether or not our molecule is charged or whether it's neutral, depending on which one we've decided we're implying. Charges are therefore never implied. So you will always show them. Okay? That will help you determine your implied hydrogens and non-bonding electrons, which theoretically, non-bonding electrons should always be shown, because when we're looking at organic chemistry, we're concerned about how 2 molecules interact, and the most likely thing to interact between those 2 molecules would be the electrons. So we would make the assumption that electrons are always shown, particularly those reactive ones. However, that is not the case. Okay? Nitrogen, oxygen, and your halogens very often have implied non-bonding electrons to satisfy their octet. Even on charged carbons, a negatively charged carbon, sometimes that lone pair becomes implied. Why? Because people that are advanced enough within the field can acknowledge and interpret and bring in that lone pair to use it when they need to. Okay? Unfortunately, that makes it more difficult for you to process and learn because you have to remember that. Okay? So your non-bonding pairs get a little bit questionable. Okay? I will make my best effort to always draw the non-bonding pairs. Okay? So if you have a question, you're like looking at a structure and you're like, I don't understand what's going on with that. Why is that missing its octet? Ask. Okay? Because it could very well be hydrogens or it could be lone pairs. both of those can be important things to identify. So if we go backwards real quickly and look in that lower right-hand corner, this molecule has no charge, which is a good thing, because according to our formula, what was the charge? Charge will always be specified in the upper right-hand corner of every formula. Go back to Gen Chem, that's all they do. That's where the charge is. Okay, so there's no overall charge on that molecule. Okay, so that's nice. The next part is dealing with our hydrogens. So if we take a look at this point, actually let's look at all our points. 1, 2, 3, 4, 5 points in blue. 5 points means 5 carbons. Matches my formula. If I want to go through and identify the hydrogens within this, right, let's take a look at the lower left-hand corner. So that carbon, I have 1 bond shown. That would mean only 2 electrons to the carbon. That's not allowed. So to get to the octet, it needs 3 hydrogens. So there's an implied CH3 there. Okay. The middle carbon has a hydrogen. The next one over has 2 hydrogens. And the ones at the end each have 3 hydrogens. Trust me, those say H's. Okay. And if we went through and totaled that up, that's 3, 6, 9, 12, C5H12. Kind of makes sense? Okay. So what do we do with this? Almost what do we do with this? So after we go through all of Lewis structure and do all these practice questions, what we should end up with is roughly this summary. You should find with enough practice that if you have a positively charged atom, depending on what atom it is, it's going to have those bonding characteristics, okay, and that charge. This means when you see an atom like carbon with only 3 bonds, okay, that should be a red flag that something weird is going on there. Maybe you forgot the positive charge, or maybe there's a hydrogen there. Okay? That allows you to go back and more critically evaluate what you drew to identify that correct position. Okay? Same deal applies for the neutral states and for the negatively charged states. Okay? So the 2 recommendations I go through with this, and this goes back to formal charge too. So once you've drawn a structure and you're like, it's absolutely perfect, the last step of all Lewis structure, and I'm going to yell about this all the way through second semester, the last step of Lewis structure is formal charge. If you can't look at the structure and say that atom is negative, then you need to calculate it. That's the whole point of making you go through and do the calculations, so that you get sick and tired of, number 1, drawing Lewis structures, so you memorize the patterns. Number 2, sick and tired of calculating formal charge, so you memorize the patterns. Right? If you outright go to memorize the patterns, very often you don't memorize them, period. Right? That's where the practice comes in. It helps it stick. Okay? So make sure you're aware of that. Make sure you're aware of those patterns. I do see people taking notes. It looks like you're trying to copy down the table. I will again point out that all of these slides are on Canvas. If you need help with that, let me know and I'll direct you to them later. Which gets us into our next section, which I believe is officially the next chapter, which I'm hoping to finish today. The roots of all functionality come into this kind of table. Okay? What is this table showing? The electronegativity of all our atoms. Okay? And so what we're trying to do is look at how that balance of electronegativity between 2 atoms interacting with each other changes their types of interactions. Once those 2 atoms have interacted, we can now bring in a 3rd atom and say, well, how does that interact with those 2 atoms? Okay? That's it. That's OChem. 2 atoms, 3rd atom. Done. Okay? Well, what about all those other big things that are drawn there? Those big things that are drawn there are only drawn there because students look at those and get confused. They have nothing to do with the overall picture. Find your 2 atoms, find your 3 atoms. That's it. evaluate what's happening with those. Right? So everything is striving for neutrality. Okay? And this is going to end up generating our charged species and how those charged species can interact with each other. Right? So if I take two atoms and I bring them near each other, say hydrogen with a carbon, okay, is that going to generate a different interaction than a hydrogen with a nitrogen? Why? Why is that different? Right? We could look at size. Good idea. Size is important. Is hydrogen different than hydrogen in size? No. Okay, so your size argument is starting to fall apart. But we didn't talk about carbon versus nitrogen. Is there a size difference between carbon and nitrogen? Not really is the safest answer on that. Remember what we talked about at the very beginning of the semester? No. Within a row, there's not a significant difference in size to have any effect. So when we look at hydrogen versus carbon and hydrogen versus nitrogen, size does not contribute. Right? So is there a difference then? Is there a difference? There's a big difference in electronegativity. Nitrogen is a 3, carbon's a 2.5. Okay? That difference in electronegativity changes the polarity, if you will, of that bond. Okay? The hydrogen starts to become positively charged in the case of the hydrogen-nitrogen, which then makes the hydrogen reactive. Okay? Because the activity or reactivity has changed, what happens? We name it something else. So a hydrogen carbon gets named as an alkyl. Why do we pick alkyl? Because amine was already taken. Okay? That was supposed to be sort of funny. Hydrogen with oxygen, we've defined as hydroxy. Horrible term, by the way. Okay? And maybe we'll address why later. H with Cl, I got nothing better than acid. Because when we bind hydrogen to chloride, we have hydrochloric acid. There's nothing else to it. That's not organic chemistry. Okay? What happens if we take carbon and we bond it to carbon? Okay, is that different than carbon bonded to hydrogen?
Yes.
Why is that now different? Okay, neutral in electronegativity. But hydrogen to carbon was neutral in electronegativity too. That's why they were both nonpolar covalent bonds. What is the difference between hydrogen and carbon versus carbon and carbon? It's a hint, it wasn't electronegativity. But I'm only referencing that one bond, so I don't accept that. It's true, but that kind of goes back to the bonds. Interesting idea. A greater number of protons. We'll find that most cases will ignore the nucleus. What happens when you increase the number of protons? You increase the number of neutrons, okay, but both of those are found in the nucleus, and we said we'll ignore the nucleus. What happens when you increase the number of protons? You also increase the number of electrons. What happens when you increase the number of electrons? It typically gets bigger. It didn't get bigger across a row because they're in the same row, same energy level. What's the difference between hydrogen and carbon? They're in different rows. There's a size difference now. Okay, so we can evaluate a difference there. Okay? The carbon-carbon gets called our alkane. The carbon-nitrogen gets called an amine. Interesting. We start to see a cycling of the names. Why do we see that cycling of the names? The size difference, we've decided, isn't a large contributing factor. We're more concerned about the electronegativity difference. Okay? Carbon versus oxygen, alkoxy. Ooh. Oxygen to hydrogen was hydroxy, and now I'm alkoxy. Why did the name all of a sudden change? The chemistry of the carbon-oxygen bond is drastically different than the chemistry of the hydrogen-oxygen bond.
As the #1 choice of hospitals.
Right? Carbon to chlorine gets referenced as a halo. Okay, so we start to acknowledge those different functional groups, which then means we have to know what functional groups are available to us. Okay? We can introduce this idea of pi. Notice that we have sigma and pi written in on both of these, or on all of these. Sigma, as far as you're concerned at this point, stands for single. Pi is also just a single bond. That's kind of weird. Okay? But if I have a pi and a sigma, I now have a double bond. Okay? I can only get the pi after I've achieved the sigma. Can't eat your pudding unless you have your meat, right? Okay, that's another old reference. Sorry. Okay, carbon to carbon, pi bond gets called an alkene. If I add a second one, it's alkyne. Carbon to nitrogen, imine. Carbon to oxygen, carbonyl. These are the root functional groups. Okay? They all get different names because they contribute different reactivity. What happens if I put one functional group near another functional group? Should that change the chemistry? Maybe. Let's take a carbonyl, carbon-oxygen double bond, and let's bond that next to a carbon-oxygen and an oxygen-hydrogen. Anybody know what that functional group is called? A carboxylic acid. Is that chemistry drastically different than the individual pieces that made it up? Yes. That's actually acidic. The other ones don't mention anything about acidity. So when we start to combine multiple functional groups, we can generate new functional groups. So yippee, the more we combine, the more functional groups we have to deal with. Okay? Could we combine 3? Yup. Okay? Will that generate a new functional group? Yup. Okay? So there's tons of different possibilities that can come out of this. Okay? For the most part, I would argue that these are the primary ones you need to be concerned about. Right? When? For the entire year of OChem. There are other functional groups that pop up, but for the most part, this happens to be the big ones. These also happen to be all the ones, that you'd be responsible for naming. Okay? Other functional groups, you're responsible for acknowledging their existence and being able to look at it and say, yes, that's an acetal. I have no clue how to name it, but I at least know it's an acetal. I don't know what an acetal is? Perfect, it's second semester, don't worry about it. Okay? So these are all the functional groups that you're expected to be able to name. Okay? So when you look at a compound that contains them, you have to be able to put that together. Okay? That's where our textbook has an advantage, because it just says, here's all the rules for nomenclature, use them. That's the individual nomenclature chapters. Okay? How many of these do you think we're going to work with this semester? I don't know. I always forget. Okay? Pretty much that first whole column, the alcohols, the ethers, yep. And that's about it. Okay? So those 2, 4, 6, you absolutely need to know how to work with. Okay? To a lesser extent, we can throw in the carboxylic acids. Okay? Any idea why we might throw in the carboxylic acids? I put 2 beakers in front of you. One of them has water, one of them has hydrochloric acid in it. Which one do you care about more? Hydrochloric acid. Why?
Because it's a deadly chemical.
It's a deadly chemical. Why are we concerned about carboxylic acids? Because it includes the word acid. Yes. So when we're looking at reactivity, we'll look at acid and base reactivity. Carboxylic acids are the key characteristic. Okay, so we'll look at that reactivity there. But we'll leave their chemistry at pretty much that for this semester. Okay? So, reaction versus interaction. Before a reaction can occur, we must have some kind of attraction. So we've got 4 things drawn up here. These are 4 separate categories. Okay? I want to define the interaction now between sodium chloride molecule A and sodium chloride molecule B. Which of those interactions is the more likely interaction? Why the top one?
Because the other one, it doesn't cancel out. It actually makes it more unstable.
It doesn't cancel. What's it?
Chemical A does not.
The chlorine is two negatives. The chlorine is not attracted to the other chlorine. It's
Charge.
positive and a negative charge.
It's solely charge. How do we know there's charge within this? Does anybody see charge written on any of those things? No. How do you know there's charge? Metal and a nonmetal, meaning it's an ionic bond. Which one's charged? Both. What charge do each hold? Sodium is positive. Chloride is negative. How do we know that? So one way is officially looking at oxidation number. Let's just say no, ignore. It's not no, but let's just not do that. That's a dangerous path. Let's avoid that. Someone, what did you guys say back here? We could look at bulk reactivity of our metals typically generate positive charges. Non-metals typically generate negative charges. Why?
Because sodium's got one valence electron, so the completest octet is easier to lose that.
Electronegativity is why. This is why electronegativity is important. Why does sodium carry a positive? Or why do our nonmetals typically carry negatives and our metals typically carry positives when we put them into bonds? Okay? Well, the metal electronegativities are all sub 2. We get some weird ones floating in the middle, but for the most part, sub 2. All of our nonmetals are greater than 2. Which means all of the nonmetals in a bond between a metal and a nonmetal are going to do what? Take the electrons, which then means the metal becomes positive, the nonmetal becomes negative. It's electronegativity. It's what dictates what happens here. So that when you go back and look at your interactions, what you're using to establish the sodium is positive and the chloride is negative is a difference in electronegativity. That's what generates that interaction. And we look at the bottom one, that would be a negative to negative. That doesn't neutralize charge. That's a crap decision. So we do the top one. How about carbon to hydrogen? Sorry, I just erased all that and had it reappear. Which interaction is now favored? Top or bottom?
Actually, it almost doesn't matter with this one.
Hearing a lot of tops. Why are you saying the top?
Because that's what we were taught.
Charge. What's the charge by definition in the bond between carbon and hydrogen? Carbon to hydrogen is by definition a nonpolar covalent bond, which means what is the charge established on either ends of that bond? Neutral or zero. Well, if there's a zero charge, which of those interactions is more favored? Well, the favoring comes from neutralizing the charge. There's no charge. So how do we decide? They're both roughly equally valid. Okay, there's other things that contribute, like where those atoms are located, separate issue. Okay? But there's nothing to really drive this. Okay, which brings in the next issue. Would I expect this interaction to be weak or strong in comparison to the sodium chloride one? Should the sodium chloride be stronger or weaker than the carbon-hydrogen interaction? Why should it be stronger? The sodium chloride is actually neutralizing charge. It's saying, I'm negative, cancel me out. We need to be partnered. The bottom one, what's happening? They're neutral. There is already no reason to interact, which is why there isn't an interaction. At least that's our first guess. Okay? Then some jerk off, probably a physicist, let's just call him a physicist, comes back and says, actually, it is kind of important. Who was that guy? van der Waals, who found out that that interaction does account for a lot of observable phenomenon, typically in gases. So that interaction is known as the van der Waals interaction because it comes from the guy who discovered it, also known as the London dispersion force, or induced dipoles, whatever you want to call it. It's getting at a really horribly weak interaction. What about the top interaction? What do we want to call that? Ionic. Why? Well, the bottom one came from whoever discovered it. So the top one was discovered by ionic. You all guessed that top one was correct. You had a lot of trouble with the bottom one. Okay? In fact, we had a lot of trouble and said, actually, you know what? It's not important. So we as a populace said, it's irrelevant. Somebody important comes along and says it's not irrelevant. Guess what? He gets to stamp his name to it. You all got this one right on the first try. If it's easy, you don't get to attach your name to it. Okay? And it gets attached to the origin of where it came from, which was an ionic bond. Okay? So we could call it an ionic interaction. Why has that become problematic? Both of them say ionic in it. So we can call one an electrostatic force and the other one an ionic bond. They're referencing different categories. All of the interactions that we see come from looking back at our individual atoms, there's our two atoms, interacting with a third. Okay? How does that interaction rank as far as strength? Is that important enough for us to label or even acknowledge? If it is, we're responsible for it. Okay? What if I change sodium chloride to be sodium fluoride? Is this still ionic? Okay. Is it a strong an ionic interaction?
Yes.
Ooh, there's fun. We got a yes and no's from the audience.
Maybe a little bit stronger since.
Why is this one now stronger? There's a greater electronegativity difference. Okay. What if I switch this from sodium to, sorry, that was not the pen I thought it was. Rubidium. Does that change the interaction? Yes, by small gradations. The point to this is that all of our interactions are a continuous spectrum of interactions. The analogy I go back to is the rainbow. What colors are in the rainbow? Roy G. Biv. Okay. What is the color between red and orange on the rainbow? Is there one?
Red, orange.
Red, orange. Okay. Do we have somebody with a better descriptor than that?
There's a color called that. There's a crayon that color.
I know it's called that. Give me a better crayon color. What's the color between red, orange, and red? We have red, red. We have red, orange. We have red, red, orange. We have red, red, orange, orange. Well, that one's probably just red, orange. Red, orange, orange. We have variations within each of those because what colors are in the rainbow? All of them. What interactions are possible? All of them. But we have gone through just like we did with the rainbow and said, roughly within this box it's red, within this box it's orange. What's in between those? We just won't tell people to memorize that. Okay? Same thing is happening with our interactions. Okay? When we go through and look at our interactions, okay, we have covalent, polar covalent, ionic, electrostatic, hydrogen bonding, dipole-dipole, and London dispersion. Those are our equivalents of, actually, red, orange, yellow, green, blue, indigo. Oh, wow, cool. That actually matches. I'll remember that next time around. We have our Roy G. Biv of intermolecular forces. Okay? That's these boxes. Does that mean there's nothing in between? No. There's absolutely something in there. We just decided that it's in too much of a gray area for us to box in. But can we still work within that? Can we still draw conclusions and label Jeremy's shirt as red? Right? I labeled red from the rainbow, and now I can say his shirt is red. Or Gemma's shirt is red. I can use that information. Same thing is happening with all of our intermolecular attractions. Okay? And we divide this into two categories. right, which we didn't do with the rainbow. Right? We've got the intra, or within a molecule. The attraction is now so strong that it makes a bond. Or we have the inter. The attraction is not fully there where we're making a bond, but it's strong enough that there's some kind of force attracting those things to each other. Right? And we use that to then categorize. The part that's useful out of this is that if you have an intramolecular ionic bond, that will generate an electrostatic intermolecular force. If I have a polar covalent intramolecular bond, that will generate a dipole-dipole force. So by looking at the structure, where I can see the bonds, I can label the forces. Once I know the forces, I can now start to predict how that molecule is going to interact with other molecules, and that's pretty insanely powerful. Okay? That's where we get our melting points, our boiling points, solubilities, vapor pressure. They also contribute to all sorts of reactivity. Okay? I personally really like this diagram, and not just because I made it, because what it's trying to show is the full spectrum of our color wheel. If I have a tealish polar covalent bond, that's going to result in a tealish dipole-dipole force. Okay? It allows me to see the relationship across that. It is still a continuous spectrum. Okay? All of the physical properties that we see in our world come from the forces. Those forces ultimately originate in our bonds. And this is where we can encounter some weird things. Okay? For instance, methane, CH4. Actually, do I want to go there? Let's not go there. Let's not do that, because I think I got other examples that are more relevant. Right? So when we're looking at a melting point, the stronger the force, the higher the melting point. Same deal for boiling point. Solubility, the more similar your forces, the more likely they dissolve. Vapor pressure. Okay? Don't worry about vapor pressure. Okay? All of these kind of contribute and stack and interact with each other. You're responsible for looking at them, acknowledging them, and using them. Okay? So melting points. Okay? A melting point is the energy necessary for a phase change. What resists that phase change? What resists a phase change? It's the intermolecular forces that prevent that phase change. Okay? So if we're looking at species that have higher melting points or lower boiling points, we can try and manipulate this. So now let's try something. Let's take a look at sodium chloride. And since everybody said forces, maybe this won't be as fun. Sodium chloride versus methane. Everybody know phases for those? Don't tell me, but you all know the phases for those? Is that a yes? You can tell me yes, just don't tell me what the phases are. Okay. We got enough yeses to move on with this. Okay. Which of those two compounds has the strongest bond? I heard pretty universally sodium chloride has the strongest bond. Okay, why are you saying it has the strongest bond? Okay, so ionic bonds are stronger. Stronger than what? They're stronger than covalent bonds. Is that what you're saying? What happens when I add water to both of these compounds? What happens to the bond between sodium and chloride when I add water? It breaks, it dissociates. What happens to the bond between carbon and hydrogen when I add water? Nothing. But I thought you said sodium chloride has a stronger bond.
sodium chloride just more polar, not necessarily a stronger bond?
Okay? This is where we have to be very careful in our references. It is not the strongest bond. It is actually the weakest bond. Okay? And I would bet why you wanted to say sodium chloride had the strongest bond had to do with the phases. What was the phase of sodium chloride? And the phase for methane? Gas. So why does that mean sodium chloride should have the strongest bond? Well, it's a solid, right? So that means it should have the strongest intermolecular attraction. The intermolecular attraction is an ionic bond. That's confusing. So let's get rid of the word ionic bond and let's switch that to electrostatic. The weakest bond because it's an ionic bond. Okay. What is the intermolecular attraction for CH4? I tell you, it's not covalent. Covalent is the intramolecular attraction. What is the inter-attraction for CH4? Some people are pulling it out. It's the London dispersion force. CH4 has a stupidly strong bond. Okay? It is insanely strong. Both of those atoms are equally sharing their electrons. Okay? Electrons are existing between both atoms evenly. In sodium chloride, are they sharing electrons? No, because it's an ionic bond. By definition, they don't share. Okay? So why then would CH4 be a gas? Because that's saying it has a very weak attraction between the molecules. Oh, wait a second. Between the molecules. But when I look at CH4, what am I looking at? The atoms within a single molecule. If I'm going to look at the phase, I need to look at the force. The force for CH4 is London dispersion. The force for sodium chloride is electrostatic. Which is the stronger force? Electrostatic, even though it has the weaker bond. And in fact, because it has the weaker bond, it has the stronger force. When we move to CH4, it has an insanely strong bond, which is why it has an insanely weak force. There's no reason for it to interact with the world because the bond is so strong. Okay? So we have to kind of make sure we reevaluate when we're looking at our physical properties. The physical properties are force-based, not bonds. Okay? And for those of you in lab where you start to go through and describe something and say, well, the bond is stronger, you will have me yell at you. Nicely-ish. I might just stare at you and be like, oh, forces. It's cool. Okay? It's the force that you need to be evaluating. The force comes from the bond. Okay? The other one we can look at is solubility. Those of you in the lab also have some fun exposure with solubility. Because when we talk about solubility in Gen Chem, it's like they just do. Because that's the way it works. Okay? It's a spectrum of interactions. Because it is a spectrum, depending on where we fall on that spectrum, the difference between those can be pretty dramatic. And can result in things being soluble or not. And in Gen Chem, at best, they give you a numerical value. And say, well, the difference between those is now greater than the threshold, so it must mean that they're insoluble. Okay? Well, the fun part with that is they gave you that numeric value. How long did it take to find that single numeric value? Probably days of calculations. And then you have to get it for the other substance. So in 2 days, you've got enough data that you can calculate without a doubt the solubility for 2 different compounds. Or you look at them and be like, yeah, they're pretty close. I think they're going to mix. Okay. OChem, yep, they look pretty close. Gen Chem, let me spend 5 days and I'll tell you for sure. Okay. Organic chemistry is very much, yeah, I think it's going to work. Mix, yep, it worked. We're done in 5 minutes and we leave. Gen Chem wants to get the exact numerical answer behind it. Okay? They're both valuable, don't get me wrong. But Gen Chem sucks. Okay? It's just looking at different applications. Okay? Gen Chem will always be right. OChem, maybe 70% of the time we're right. 70% of the time is still a pretty solid pass. Right? So it comes from where our individual thresholds are. Okay? So our big rule of thumb from solubility, which is going to become a big player, like forces dissolve like forces. So let's get into our solubility. In solubility, we have two things that we're evaluating. What are those two things that we evaluate? This is a review. One of them is on the board, by the way, or on the screen. They both begin with S.
Solvent.
Solvent, yes, and solutes. Okay, we're talking about mixing solvents with solutes. Okay, well, solvents tend to be our bulk one that we deal with, the most, so we add some terminology to help us kind of classify these. So you will hear the terms polar versus nonpolar. I personally hate polar and nonpolar because those two words, depending on the rule set that you use to define them, can cause a compound to be polar or nonpolar. The exact same compound gets two different classifications. I find that insanely frustrating. Okay? So our polar versus nonpolar at best is referencing the bonds that are present. Why is that problematic? Solubility is looking at forces, not the bonds. The bonds lead us there, but they don't take us all the way. So use the terms polar and nonpolar sparingly. Okay, what we're identifying is highly electronegative atoms being present, polar, or not electronegative atoms being present, nonpolar. Okay? That gets us 2 boxes. 2 boxes is nice, but we want more boxes. So we'll add in these 2 terms, protic and aprotic. Prot sounds an awful lot like proton. What do we know about a proton? It's a positive charge. Do we know anything else or know any species that are just a proton? A hydrogen atom, minus its electron, so after it's been released by an acid, is a proton. Okay, so a protic solvent is actually referencing the presence of a positive hydrogen. Okay, so all of our acids are by definition protic solvents because they release H+. But do you have to be an acid to have a positively charged hydrogen? Said another way, can you have a partially positive hydrogen and be not an acid? I don't think that was any clearer. Yeah, water. Water gets us partially positive hydrogens. Right? And if we're in the proper environment, water will give up a proton. It will act as an acid. So we can reference that compound as a protic solvent. Water is the classic example of a protic solvent. Okay? And by being protic, it has a partial charge, which then means by definition it will also be polar. So we can then subdivide out our categories now to be polar protic, polar aprotic, nonpolar protic, or nonpolar aprotic, right? We just fill in all our matches. Did any of those that I just listed make no sense? Should I say them again? Yeah. Polar protic, polar aprotic, nonpolar protic, nonpolar aprotic. So 4 boxes. What does nonpolar mean? No charge. What does protic mean? Positively charged hydrogen. You cannot have a nonpolar protic solvent. It doesn't work. Okay? So we end up getting 3 categories coming out of this. We have polar protic, We have polar aprotic, and we have nonpolar aprotic. Okay? That's still an awful lot of words. If I'm protic, what am I by definition? I'm by definition positive. So I could just go through and say protic is polar. So I can just reference my solvent as protic. That's going to imply the polar. Okay? An aprotic solvent, however, could be both or could be polar, or it could be nonpolar. So I really get three categories that I can drop my solvents into. That can help me now decide what different interactions I'm going to see. Kind of make sense? Okay. Which I think is going to get us to a quick example. So let's take a look at this quick example. Let's take a look at that first compound. What do you think? Which box is that going to fit in? Protic, polar aprotic, or nonpolar aprotic? There's hydrogens in there, right? So if there's hydrogens, it's got to be protic. Then they'd all be protic. Every solvent would be protic. Why the hell do I have more boxes? Good question. Just because it has hydrogen, does that make it protic? To be protic, what did we need to have? A partially positive hydrogen. Are those hydrogens partially positive? Why not? They're connected to carbon, and the difference in electronegativity between carbon and hydrogen is by definition the same. So there we go. That first one cannot be protic. So what does that make it then? Aprotic. Polar aprotic or nonpolar aprotic? Why is it going to be polar? We have the second most electronegative element on the periodic table in our compound. If there's extras, just keep them at the side. Okay? That's going to make that first one polar. Let's do PA. PA works. Polar aprotic. How about the next one? Polar protic, because we see the OH should immediately be a tip-off. Okay, the next one. OH is immediately a tip-off. We have polar protic. Last one. Now nonpolar aprotic. Okay? So we will use these solvent classifications again and again and again. We can use it for our solubility because we could look at a compound and say that compound is more polar-esque or more protic. I want a protic solvent to dissolve that compound. So by identifying the forces and matching the forces up, we can classify a little bit better. So, what is this little piece of paper for? So turn the paper. I want your name at the top. Cut a line through the middle of it. And by cut, I just mean draw a line through the middle of it. Okay. 1 and 2 above and 3 down below. That's it. Just name, 1, 2, line, 3. We good?
I put the line the wrong way.
Okay. Which gets us to our quiz. Okay. Oh my God. And maybe as we go through and do it, maybe you'll pick up what's going on with questions 1 and 2. So I'm hearing a lot of reference on size, the number of particles, complexity, the branching. All of those terms do contribute to or to your different phases. The interesting thing about those terms is those are all secondary effects. Okay? The primary effects would be intermolecular forces. You mean like the intermolecular forces we literally just spent an hour talking about?
Yeah.
Yes. The quiz is based off of what we just talked about. Try applying what we just talked about first. Okay? And it could very well be that I would be just being a jerk and making it more difficult for you. But try to make life as simple first, then make it more complicated if you need to. Okay? So the first approach would be going through and identifying the intermolecular forces, because maybe something triggered here. Okay? So someone just happened to be asking as I was going to go back through and start drawing this, so we picked B and C. Right? And they were trying to figure out what the difference was between them. So the first thing they did was identified that in the OH bond, we would end up getting hydrogen bonding as an intermolecular attraction. The OH bond is a polar covalent bond, which leads to a dipole-dipole force. But because I have hydrogen bound to oxygen, nitrogen, or fluorine, I have hydrogen bonding. Okay? But I have that in both cases, which then means, well, I'm SOL. That didn't help me classify, okay, because they're the same thing. So what do I have to do? Go to the next thing. Find the next thing that is different between them. Okay? Don't just give up. Find the next thing that's different. Well, the next thing we see here are carbons and hydrogens. Oh, just a bunch of carbons and hydrogens. Well, that's non-polar covalent. That's London dispersion force. Well, that was boring. I don't know why you made me do that. Well, in the next one over here, I have carbon, London dispersion. Oh, but I got this carbon to oxygen. Well, that's polar covalent. Well, that's a dipole-dipole force. Dipole-dipole versus London dispersion. Dipole-dipole is a stronger intermolecular attraction than London dispersion, which would suggest C should be higher than B. Is it perfect? Who cares? We have an explanation that goes through this. Okay? It holds to theories that we understand and can trust. Okay? Whether or not it's perfect, we'd have to go into the lab and test it. And guess what? We're right. Okay? That's where this is beautiful. We can look at these structures and come to these predictions without having to do massive, complicated calculations. We move to the next one, A. Okay? We look at its forces. Hopefully what you should identify is that it has a dipole-dipole force as its strongest force. Okay? In D, its strongest force is London dispersion. Okay? Now that you've got forces, now you can start comparing, which brings in the other question. When we started this whole thing off, I said compare B to C. I did not say compare A, B, C, and D. All comparison questions, and this is something that tends to freak students out when it comes to comparisons. You see 4 things, and you immediately start saying, well, it must be B, C, D, A. No. It's A and B. And then I'll compare C to B, and then I'll compare C to A. Now I know A, B, C. Okay? Then I'll bring D and compare that to C. Then I'll bring D and compare that to B. And then I'll be D and bring that into A. Okay? All comparisons, all rankings are not ranking 4 things at a time. They're ranking 2. Stop ranking 4 things. Rank 2. I don't care what 2. You need to rank all of them eventually. Start with 2, figure out your ranking, make it more complicated as you need to go. Okay? Move up to the solids. Okay? Because if I'm going to look at homogeneous solution, that's solubility, I need to make a mixture. Okay? That means like dissolves like. I need to know the forces. I've got them for the liquids, I don't have them for the solids. So if we apply them for the solids, we should end up with LDF, hydrogen bonding, dipole-dipole, and this last one always seems to throw people for a loop. Admittedly, I know why, but it's okay. Well, it's okay in my mind. What does that symbol mean? It's a cat, which means the interaction we're going to see there is okay, just kind of drawing a flag to it. Okay. So if I want solubility, I want the ones that best match. Okay, just LDF. Should one match to A? No. One match to B? No. What should one match to? D. So I would say 1D. Okay. 2 is hydrogen bonding. Okay. 2 gets tricky because there's 2 hydrogen bonding options. Which one's right? They would probably both be equally valid. You could go through and say 2B, or you could go through and say 2D. They're both hydrogen bonding solvents. We might lean towards 2B because it is most similar. After hydrogen bonding, the top one really just generates that dipole-dipole. There isn't a second polar force.
You meant C.
Yeah. Just because you know your alphabet, don't rub it in. But yes, you're right. It's 2C. 3. Okay. Dipole-dipole. C has dipole-dipole, but it also has hydrogen bonding. Okay. A just has dipole-dipole. Really, 3 could probably work with A, B, and C. All of those would probably work. You mean there's multiple answers? Yes, there's always multiple answers. Okay. All you need to do is put 1. Then good for you. Let's put it this way. I don't want to write more than 1. So I'm just going to write 2A, 3A. 4, ionic. None of those really match, so one option is be like, none of them are ionic, it's not going to dissolve. Okay? But it says most likely. Which of those is most likely to do it? Why would you list C? C has the strongest forces. It has both hydrogen bonding and an extra dipole-dipole. A just has the dipole-dipole. Okay? This is a doozy. This is trying to get you to think outside of your box. Find those overlaps. Sorry, I want to walk away so you can talk to each other. Okay? Okay. Why does this become important to us? Well, it comes in with applications. If we take a look at these 2 reactions, okay, both of these are showing the exact same result with the exact same starting materials. Whoops, not showing the exact same results. Okay. One is saying the chloride comes in, attacks, and kicks out the iodine. And the other one just says the iodine gets kicked out. Okay. They're both kind of doing the same thing. Iodine gets kicked out of the structure. Okay. But it's how the iodine gets kicked out that changes between these. Okay. Does the solvent play a role? Yes. A huge role. Depending on how we decide to get that iodine kicked out, I want one solvent but not another. Right? So being able to look at and classify a solvent and what's happening within a reaction. Notice, what do we have here? That looks an awful lot like an arrow, and it also looks like it's curved. You mean kind of like resonance arrows? Yes. Why are these not resonance arrows? It's not showing resonance. Touché. Try again. We're not moving electrons. This line starts in a single bond, and a single bond has electrons. So we're moving electrons. This one, the line started at the lone pair. We're moving electrons. Why are these different than resonance? Okay. That big curved arrow from the chloride, we might say, well, that's kind of like moving what we did in resonance. But the other arrows, not so much. Because in resonance, I was only allowed to move multi-bonds and non-bonding pairs. Here, I'm moving sigma bonds. What am I doing? I'm breaking a sigma bond. Not allowed to do that in resonance. These are now mechanistic arrows. We use the exact same arrows for resonance as we do for mechanistic arrows. So when I said the resonance arrows are important to understand how they move, yes, because that's how we can explain how reactions work. We use the same ones. So learn your resonance arrows. When we move into reactions after spring break, the arrows then will make a lot more sense. Okay? And with that, we really have to be done. So we're going to go ahead and stop. We'll look a little bit more at some of those on